Hello, everybody, and thank you for joining this webinar. And I will talk about titanium recycling today. First, let me share the PowerPoint I want to go through today with you. So I must say, I guess my title of my talk, the title of my talk is inspired by a book written by Kathleen Housley, which is Black Sand, the History of Titanium. And in her book, she stated, and I quote, that it took some of the best metallurgical mind in 20th century to turn black sand to titanium. And in fact, this is now is it took many years to be able to extract it and commercialize it and also utilize it for, especially for aerospace application. And this has happened in 1945 when William Kroll from Luxembourg invented Kroll process, which is a made a revolution in titanium industry. I must say that titanium life compared to human life, if we allow to do that, is not being an easy life for titanium. If we, for example, if we talk about the human life, since its labor, childhood, teenager time, employability, family making and retirement, which is recycling for titanium, we are comparing the titanium into its extraction, processing, utilization, application, and which is kind of retirement. So I'm hoping to take you through that journey in this short time, starting with the labor stage, which is extraction. So one of the major problems with the titanium extraction is titanium has got by nature high affinity of oxygen, and that's caused a huge problem and make titanium extraction very expensive. And the most common mineral or oxide you can extract titanium from are rutile and ilmenite. As you see it from the screen, rutile is contain 95% of titanium dioxide, and this is the starting point of most titanium metal production, while ilmenite contain 50 to 60 of titanium dioxide, and combined with iron, which is make the extraction a little bit more difficult. So, and titanium is the ninth most abundant element on Earth. So is to get a pure titanium is very, very expensive. Now, with the rutile and ilmenite, let me get my pen, which is I like it to get the pen when I'm talking. Now, if you get the rutile, the vast majority of rutile is come from Australia, and also a very reasonable portion of ilmenite is come from Australia as well. And that's compare the amount is coming from the South Africa, Canada, and China and Ukraine. So one of the facts is titanium is being motivated since 1950 by aerospace industry. And by looking at the market share in 2016, you will see the global titanium mill, 37.5 nearly, is being used by commercial aerospace, and about 11% by defense, and the rest by the industrial or consumers. So a large amount of titanium is being used by aerospace, and that's why I'm motivated since 1950 to be used. So I'm taking you through this type of processing. Let's start with the extraction. This is a labor stage for human being. We call it sponge production, which is very known in titanium industry. So as I said, has a very high affinity for oxygen. So to react with the oxygen, it go back its nature and making this type of oxide, but also has a huge tendency to absorb interstitial element like nitrogen and hydrogen. So these type of element, when they are inside the titanium, they make a huge the microstructure evolution and also the mechanical property, because they are, for example, oxygen is alpha stabilizer, which is, I'll not talk about this today. So they are changing the structure, the composition, and hence the property of this alloy. So controlling of these elements is very, very essential. And because of high affinity of oxygen of titanium, titanium cannot be directly reduced from the source side. And that's why is going through 4 stages. So the first stage is chlorination, which you combine the titanium oxide with chloride and of course you mix it with the cork here. So what will happen, you taking the oxygen by the cork, so you will have more carbon dioxide, and leaving the titanium to react with the chlorine. So that's what the chlorination, and this is very expensive as well, because you have to do it in inert atmosphere, argon or nitrogen, and this is very, very expensive. However, after that, the second stage, you purify the titanium through the distillation, and then the major part of the advancement of titanium extraction is from when William Kroll invented Kroll process. And that's what, now we have the titanium combined with chlorine, right, with chloride. So how we get rid of the chloride now? What he did, he suggested to have magnesium. Then the magnesium will react with the chlorine. It will leave the titanium alone, and that is expensive part as well, because you have to do it around 800 to 850 degrees Celsius. And then the fourth process, it will be the leaching process, because you want to get rid of the magnesium and magnesium chloride, and you do that by leaching process, which is done in hydrochloric acid, which is again toxic, lighter, and also environmentally not friendly. And since then, Kroll process has been progressed so many, from the reaction, from the temperature, from the processing, and now is not very desirable because it is very toxic. Environmentally is not very, but at the time it was a huge revolution in titanium industry. And then from that we'll have the sponge. It will be generated, and the sponge, as from its name, is like kind of a lot of porosity in it and so on. Then after that you will go through, you will have the sponge now, then you crush it and resize it to around 2 centimeter, 1 centimeter, 3 centimeter typical size, and you produce a granular for titanium alloy. Why we do that? Because we want to make electrode out of it. And how we do that? We have the titanium granular, and then you blend it with the master alloy. For example, if you talk about titanium 6-4, you put the vanadium and aluminum and so on, or any other type of alloy element you want to do, and then dry press it to form a compact. And then these compacts are welded together through, for example, plasma welding chamber using, and then you will have the electrode. However, one important point for recycling point of view, from this you will bring the scrap to put it in the electrode and do welded with the extracted part. And since its production, the titanium recycling started. So that's important. So because it's very expensive to extract, even from its smelting process, you will bring the scrap part, because it's very expensive, very precious. So your recycling starts from its smelting process. That's it. That's why you don't see much of this type of titanium alloy. Now, what you have here, then you'll go through the even more expensive part, which is vacuum arc remelting. And vacuum arc remelting, I don't want to go through today, but you will have the electrode is being generated, and you put it, the entire system should be in vacuum, because titanium has got a very high affinity of oxygen. Then you connect in a power supply from the electrode and also the copper crucible, and you are generating a huge arc between the electrode and also the molten part on the lower side of the copper crucible, and then you are remelting. One of the problems is that, sorry about this, you're remelting a small part of this. So the chemical composition, it will not be homogeneous throughout the entire component you want to make. And also you cannot remove all the defect For example, hard particle inclusion, lattice phases, hard alpha 2, beta flake, which is common in titanium ingot. You cannot remove them by one vacuum arm. And that's why you do double VAR or triple VAR. However, this is very expensive. Or you can do, so this is an example, for example, how a blade bar made of titanium is being destroyed, as you will see it, by a defect generated from the VAR couldn't eliminate it. That's why they went to the cold hearth melting, where you melt it again and go through it, and then you melt the titanium alloy by electron beam or a plasma torch. So you melt in it, and then through that, sorry about this again. The skull here, it will trap the defect generated from the processing, and then the pure titanium will go back and the ingot will be generated. So either you do double, triple VAR, or so imagine this is very expensive process to go through. Now, so to recap, now we produce the sponge, we make it resize, then make it granular, then we make the electrode, and then we went through the VAR and then pulled here, then we have the ingot ready for forging. So this is, let's say, a childhood grown up till we get ready. Now the teenager time will start in comparison with the human being, because it will be forged, and then the cast structure will be destroyed to make more suitable microstructure for the final product. So it's believed that the microstructure from that stage is the initial microstructure, and hence affecting the property of the. So I'm showing this type of huge forging just to give you a scale of the forging, this kind of ingot titanium, and the people around it are comparatively very small to the ingot is being. And this is a drop hammer, or the hydraulic part for forging. And then you will go through the deformation, which is mainly rolling, and all that depends on, this is all type you want to produce optimized microstructure, and hence for better mechanical properties. So for the rolling, you will see you roll it either above the beta transist temperature or below the beta transist temperature. And I'll talk about this in a minute. And then all that, the microstructure will be affected by the time, the strain rate, the heating rate, the cooling rate of this type of processing and deformation. And then you'll go through the heat treatment, and again, it will be decided if it's above beta transist or below beta transist, for how long, and doing the controlling the cooling rate and so on, and then go through the aging. So this is for optimizing the property and microstructure of the alloy. So as any teenagers, as you see, it is a beautiful microstructure. However, it's been through the horrible time through this growing up stage. Now you will see that's why microstructure of titanium is very, very pretty. As you will see it, this is a laminar microstructure. This is what's called Bastian's microstructure, and this is a work we've done to look at how the crack propagation is going through the laminar microstructure and so on. You do huge amount of work and processing to optimize the microstructure through the heat treatment and surface modification, and importantly, for mechanical property enhancement, including an important and very critically for aerospace engineering, that include fatigue, creep, dual fatigue, and so on. Okay, and one point I want to mention before I go further on titanium is the anisotropic behavior. So, for example, even during the processing, this, unlike nickel or other material, you have the titanium at room temperature is HCP structure. For pure titanium, above 882 degrees Celsius, it will transform to BCC structure. Of course, this is good in a way. However, for the large volume fraction of the alloy used in application contain is actually HTP structure, and HTP structure, as its nature, it has an anisotropic behavior affecting the mechanical property and different direction. For example, if you roll or deform a sheet or a plate of titanium, if their C axis is parallel to the loading direction, right? So this will be very hard to deform and to roll, and that you're consuming more energy for the rolling. And that's but if you roll it along to be perpendicular to the c-axis, then that will be easier to deform and consume less energy. And that's not only affecting the energy during the deformation and rolling and so on, but also even in the service you will have the same problem, because, for example, if these lamina are oriented in for example, for the basal and prismatic slip activation, I don't want to go through this, then the credit will be very easy to go through the laminar structure. And also there is another one, during the processing you are generating macrozone, which is very, very common to be generated during titanium manufacturing. And then you will have, for example, this is a work we did on the macrozone, and then if you look at the macrozone, is a large number of grain, they have the same orientation. And that's not good for anisotropic materials like titanium. For example, when you look at the strain map, as we said, is very, very strained area. So when you look at the orientation, is actually is the c-axis is perpendicular to the loading direction. If you load it in that way, the clad will be very easy to go through the down, and they will be easily fractured, and that's the problem. So, as we said, it's very expensive alloy. Why are we still using it? I mean, it's beautiful teenager, but why are you still using it? Is it that old? No, because it's very strong material, very hard, and also the toughness is unique, and also it has got very oxidation resistance. Like for aluminum, you have aluminum is very a high affinity of oxygen to interact with oxygen, so that's why it's producing aluminum. Titanium is same. You're producing titanium oxide, a few nanometer of oxide, and that's preventing further oxidation from the surface of the oxide. So it has got very high oxidation resistance in that way. And also, the importantly, is very light. And that's a very good candidate for aerospace engineering and also for biomedical application. And relatively has a very high melting temperature. So it's allowing you to process this material at bigger field, thermodynamically speaking. Okay, so now let's go to the so what the application. This is employability. This is working time. You graduated from the university and now you're in service. Now titanium has got a lot of jobs to do. It never has got a problem for finding a job. For example, titanium for the aircraft is about 15%. For jet engine, if you remember, or if you are aware of the jet engine, I'm sure you all are. You will have most of the cold side of the jet engine is made of titanium, and that's including the blade and also the disc. And if you compare the titanium demand by Airbus and Boeing, for example, it's been increased hugely since 2000 till now, till 2015. It's like double because of the aircraft carriers and so on, especially for the civil application will be is being on demand all the way. That's why it's not very easy to have a very light alloy like this. So just to see why still we need titanium, and the alternative is difficult, because if you look at the jet engine, for example, this is a large jet engine, and I'm giving you this pictures just to imagine some of the blade is larger than a person, which is huge. So and even some disc is in a size or the height of a person. So this is a very serious problem for the jet engine to make it, which is you're reducing the thrust of this aircraft. So that's all the jet engine. So this is very, very important to me. And whatever you do in jet engine, you try to suck more air to the jet engine. So you need a much larger blade bar to suck more air into the core of the jet engine and compress it more. And then you have very high, what we need, you need very high pressure on the core of the jet engine, and with that you are having more air to come in, more combustion, so you will have increasing the temperature. What you need here to make the jet engine more efficient, have a higher thrust, you need hotter, lighter, larger engine. And by using, for example, super alloy to replace, it doesn't work because you are reducing the thrust of the engine. That's why it's very important to use a light alloy like titanium for blade bar. And in fact, there are a lot of studies to even replace some part of the side as well from superalloy to titanium alumina, especially the low pressure turbine side, and some company started adapting it. Now, this is midlife crisis, which is, the titanium has been serviced. This is I can easily associate with that personally, but here you go. This is titanium, intermediate performance for long exposure and aging property. It will be deteriorating in the surface. There will be, for example, these material are always on heavy load, very aggressive environment, subjected to fatigue, to loading, low cycle fatigue, high cycle fatigue, dwell fatigue, cold creep, and so on. And if for long-term exposure, you will face with the phase transformation, precipitate formation like alpha 2 for a very long-term project, and also like oxidation. And even it will be that vulnerable, oxygen will come and will stabilize the surface to alpha case, so it will convert in the entire case to alpha, which is much softer, than it will be much more susceptible for the fatigue. And I'll give you some example here. Now, let's say this is a retirement time. The guy had enough, and then this is how we recycle it. Now, for here in this slide, I'm depending on Professor Davis Roper from Virginia Polytechnic Institute and State University, when he collected the data based on two different geological data. One of them is estimated that there is 750 multiplied by 10 to 6 tons estimated of reservoir for titanium. Another database he used, there is a higher amount of titanium on Earth, about 1500 multiplied by 10 to 6 tons estimated reservoir based. In both one, as we said, since invention of the Kroll process by William Kroll, the titanium extraction is worldwide is increased since 1950 and is growing up dramatically. And using both database, by 2150 there will be no titanium left on Earth. That's his prediction. And importantly, if you look at this graph, you will see here the amount left from 1950, when the commercialization and utilization of titanium started, is going down, and there will be no any titanium left by 2150. Year of 2150, and the amount of the extracted will go up fully, so you don't have. But the common point between these two databases is by not very good line I made it, by 2055 the amount of extracted is equal to the amount left to be extracted. So we are in the critical stage. We consume half of it, we extracted half of it, only half left. Let's think about what we are doing. However, if you come to the recycling, world recycling has never been bad anyway, because it's very precious metal is being, as we during the ingot metallurgy, we are reducing the scrap, we are recycling the scrap. So if you look at the recycling part, is actually the titanium scrap recycling historically is very, very high, and it started its production. So even first recycling, second recycling, third recycling is always going on, because you don't want to go through the very beginning of the extraction time. Now, titanium is very expensive, as we said. It's about more than 10 US dollars for kilogram. However, if you look at it, titanium recycling rate is very high. As I said, because the titanium is very expensive, so it's been recycling of titanium started since production. So it's very high. Above 90% of titanium is being recycled. Is recycled. However, the nominal recycling rate, which is the recycling volume of titanium divided by the production of titanium sponge volume, which is the nominal recycling, is about 1%. It's very low. So, for example, compared to steel, this is come from Japanese database from this paper by Takiyada. For example, steel is about 25 in Japan, aluminum by 36, copper by 30 in Japan only, but for titanium is only 1%. So what that means? That means the amount of the rate is being produced much more than the recycling part. So we are in trouble. So probably we will get to the half-half part even before 2055. And why is that? Because titanium has a very long life in application surface. For example, if you have a blade bar, if you have a blade bar, and they normally they stay in their surface for very, very long time. So for 10 years, 15 years, 20 years, and that's why the reason we are using titanium. So their life service is very, and also the company, for example, Boeing, Airbus, when they have the strap of titanium, a blade bar will be released in the jet engine. There will be a disc will be braid. They don't put it on eBay to sell it. That's why the rate is very low, because they use it, and it will be more economically efficient to give it to the supply chain to recycle it by themselves and produce more blade bar and disc by themselves and different element to be put in. So you don't have much of the titanium alloy to be recycled, but rather very controlled because it's very expensive. And even for the biomedical application, it's a very long surface. For example, the titanium alloy used in the human body. For example, just cynically, you don't go to the funeral and say, okay, this guy, I know him, he replaced his knees when he was 40. So, okay, so he has got 8 years, did more. You don't do that. Nobody does that. So they stay there forever in there. So recycling is very limited in titanium, and it's very well controlled. However, one of the things is very well use is from the machining, from the turning. Wherever titanium, you straight away go back to the production and use it as a scrap. So that's the main problem in the titanium point. However, I'm just showing this part of, for example, as we said, Kroll process. It was a revolution in 1945. Made by William Kroll. However, this process is being very toxic and also environmentally not friendly. They're showing a large company, Electrode Titanium, as a good example. For example, using plasma and vacuum furnace, by using the strap and getting it to the plasma arc melting, then they go to the vacuum arc melting, they're using generating the ingot, and then go through the forging, and then close diverging, and then the product, and then any machining to go back to the strap to use it. Very expensive, but they could prevent the emission by 100,000 tons of CO2 a year, which is huge. And they are still producing 4,000 tons of titanium here at Electrode. That's a good example, not advertising, but this is a good example for not using Kroll anymore as this. However, the solution for example, neck shape manufacturing is very good. You can reduce the amount of waste for the neck shaping, especially additive manufacturing, turning the scrap into a metal into powder. There are many current studies studying that, and prioritizing titanium product employment. For example, additive manufacturing are using huge tons of the titanium alloy, but not for the actual part, but actually for trial and tool development for the AM machine. So these tons, they will be easily recycled, but however, it doesn't go to the real production or real utility or employability. So that's why AM is very good for recycling titanium alloy, but most of the titanium alloy and powder is used in AM are actually going for the alloy design, going for the tool development, AM machine development, and so on. And hopefully in a few decades, it will be fully directly go to the to the production line. Okay, I think that I spoke too much here, and thank you very much for listening. And I'm hoping to answer any question. Thank you very much for your time. Thank you.